ਵਿਦਿਆਰਥੀਓ, ਤੁਹਾਡਾ ਅੱਜ ਦੀ ਕਲਾਸ ਵਿੱਚ ਸਵਾਗਤ ਹੈ। ਅੱਜ ਦੇ ਟੌਪਿਕ ਵਿੱਚ ਅਸੀਂ ਡੀ ਬਲਾਕ ਐਲੀਮੈਂਟਸ ਤੇ ਵਿਚਾਰ ਕਰਾਂਗੇ। ਪਰ ਇਸ ਤੋਂ ਪਹਿਲਾਂ ਮੈਂ ਤੁਹਾਡੇ ਨਾਲ ਅੱਜ ਦੀ ਕਲਾਸ ਦੇ ਸਿੱਖਿਆ ਉਦੇਸ਼ ਸਾਂਝੇ ਕਰ ਲਵਾਂ।
On completion of this topic, learners will be able to locate the position of D block elements in the periodic table, discuss chemistry of D block elements, describe characteristics of D block elements. Children, we are looking at a D block in the periodic table. It is situated in the middle of the periodic table between the S block and the P block. The D block elements include 10 groups, that is, from group 3 to 12 of the long form of the periodic table. Now let us learn about D block elements.
D block elements ਵਿਦਿਆਰਥੀਓ, D block elements ਉਹ ਹਨ ਜਿਨ੍ਹਾਂ ਵਿੱਚ added electron goes into one of the D orbitals. These elements have valence electrons in both their outermost and penultimate shells and have a general outer electronic configuration of n-1 D 1 to 10 ns 1 to 2. The penultimate shell in these elements is expanded from 8 to 18 by the inclusion of 10 D electrons. ਇਹਨਾਂ D block elements ਨੂੰ transition elements ਕਿਹਾ ਜਾਂਦਾ ਹੈ। Transition elements ਕੀ ਹਨ? Those elements which are situated in the middle of the periodic table between the S block and the P block are called transition elements. These are called so because they represent a transition that is change from metallic character of S block elements to the non-metallic character of P block elements through D block elements which are also metals. All D block elements are classified into 4 transition series. These can be named as first transition series or 3D series in the 4th period having 10 elements. Second transition series or 4D series in the 5th period having 10 elements. Third transition series or 5D series in the 6th period having 10 elements. Fourth transition series or 6D series in the 7th period having incomplete elements. The D block elements are classified on the basis of similarity of filling of electrons in various orbitals. We will now learn about the electronic configuration of the 4 transition series. Children, let us first learn about the first transition series. This is also called as 3D series, which involves the filling of 3D orbital. It starts from scandium, whose atomic number is 21 and includes 10 elements, till zinc, whose atomic number is 30. आओ सब तो पहला first transition series और 3D series ते नज़र मारिए। तुसी elements, उन्हां दे atomic numbers, उन्हां दे symbols ਅਤੇ उन्हां दे electronic configurations देख रहे हो। Atomic number of scandium is 21. Its symbol is Sc. According to its electronic configuration, it has 2 electrons in its outermost 4s orbital and 1 electron in its penultimate 3d orbital. Atomic number of titanium is 22. Its symbol is Ti. According to its electronic configuration, it has 2 electrons in its outermost 4s orbital and 2 electrons in its penultimate 3d orbital. Similarly, for vanadium, atomic number is 23. Symbol is V. it has 2 electrons in its outermost 4s orbital and 3 electrons in its penultimate 3d orbital. Atomic number of chromium is 24. Its symbol is Cr. According to its electronic configuration, it has 1 electron in its outermost 4s orbital and 5 electrons in its penultimate 3d orbital. Its electronic configuration is exceptional. Atomic number of manganese is 25. Its symbol is Mn. According to its electronic configuration, it has 2 electrons in its outermost 4s orbital and 5 electrons in its penultimate 3d orbital. Atomic number of iron is 26. Its symbol is Fe. According to its electronic configuration, it has 2 electrons in its outermost 4s orbital and 6 electrons in its penultimate 3d orbital. Similarly, for cobalt and nickel, atomic number of copper is 29. Its symbol is Cu. According to its electronic configuration, it has 1 electron in its outermost 4s orbital and 10 electrons in its penultimate 3d orbital. Its electronic configuration is exceptional. Atomic number of zinc is 30. Its symbol is Zn. According to its electronic configuration, it has 2 electrons in its outermost 4s orbital and 10 electrons in its penultimate 3d orbital. Let us now learn about second transition series. This is also called as 4d series, which involves the filling of 4d orbital. It starts from yttrium, whose atomic number is 39 and includes 10 elements, till cadmium, whose atomic number is 48. ਇੱਥੇ ਅਸੀਂ second transition series or 4d series ਵੇਖ ਰਹੇ ਹਾਂ.
The electronic configuration of these elements shown on the screen is exceptional. The electronic configuration of these elements which you are seeing on the screen is exceptional.
Next comes third transition series. This is also called as 5d series, which involves the filling of 5d orbital. This series contains lanthanum with atomic number 57 followed by 9 elements having atomic number 72 to 80. Third transition series or 5d series. ਇੱਥੇ ਅਸੀਂ third transition series or 5d series ਦੇਖ ਰਹੇ ਹਾਂ.
The electronic configuration of these elements you are viewing on the screen is exceptional.
The next one is fourth transition series. This is also called as 6d series, which involves the filling of 6d orbital. This series contains actinium with atomic number 89 followed by 9 elements having atomic number 104 to 112. We are looking here at first element actinium of this series on the screen. Its atomic number is 89, its symbol is Ac, its electronic configuration is also shown here on the screen. It has 2 electrons in its outermost shell and 1 electron in its penultimate shell. Similarly, we can study other elements of this series. The electronic configuration of rhodinium is exceptional. Now let us learn more about transition elements. Electronic configuration. According to definition, d block elements are those which in their elemental or combined forms have partially filled d orbital. विद्यार्थियों, ऐसे दे आधार ते इस सवाल दा जवाब देने दी कोशिश करो. Do all d block elements have partially filled d orbitals? No students, it is not true. Let's see the electronic configuration of zinc, cadmium and mercury. Zinc 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2 or 2, 8, 18, 2. Cadmium 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 5s2 or 2, 8, 18, 18, 2. Mercury 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 4f14, 5s2, 5p6, 5d10, 6s2 or 2, 8, 18, 32, 18, 2. These have completely filled d orbitals. Thus, the general electronic configuration of d block elements is written as electronic configuration of noble gas into n-1, d1 to 10, ns1 to 2. Now let's see electronic configuration of scandium. 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2.
It shows that it has incompletely filled d orbital. It has only one electron in its d orbital.
All the d block elements except zinc, cadmium and mercury have partially filled d orbitals. Students, another very important point to be noted is that half-filled and completely filled sets of orbital are relatively more stable. Let's take up characteristics of transition metals. All the transition metals except zinc, cadmium and mercury exhibit several characteristics. Some of these are: all transition elements show typical metallic structure except for mercury, which is liquid. Show typical metallic properties like metallic luster, high tensile strength, ductility, malleability. High thermal and electrical conductivity. High boiling point and melting point. High enthalpies of atomization. Show variable oxidation state. Show catalytic properties. Form colored compound. Form interstitial compounds with elements like hydrogen, carbon, boron or nitrogen. Form alloys.
Look at the graph on the screen. Here, atomic number is plotted against melting points. We are looking at the atomic number of first, second and third transition series in this graph. It is clear from this graph that melting point of second and third transition series is much higher than that of first transition series. Moreover, in each transition series, the melting point increases with increase in atomic number and becomes maximum in the middle because at middle the elements have d5 configuration, which has maximum number of unpaired electrons. The melting point decreases towards the end as the electrons get paired up. Now look at this graph on the screen. Here, atomic number is plotted against enthalpy of atomization. We are looking at 3-line graphs here. Graph 1 represents first transition or 3D series. Graph 2 represents second transition or 4D series. Graph 3 represents third transition or 5D series. It is clear from this graph that second and third transition series have high enthalpies of atomization than the first transition series.
Thus, transition elements have high melting and boiling points due to the involvement of both Ns and N-1 d electrons. This is also depicted by high enthalpy of atomization. आओ D block elements ਦੇ ਇੱਕ ਹੋਰ characteristic ਨੂੰ ਲਈਏ. Variable oxidation states. Transition elements show variable oxidation states. Let's try to understand why is it so. The study of electronic configuration of transition metals justify the occurrence of variable oxidation state as both Ns and N-1 d electrons participate in bonding because of very small energy difference between these orbitals. Now, what is the reason of low oxidation state or high oxidation state? The participation of Ns electrons in bonding leads to lower oxidation state like +1 and +2. And what is the reason behind higher oxidation states? The participation of N-1 d electrons in bonding leads to higher oxidation states like +3, +4, +5, +6, etc. There is one more reason of variable oxidation states. What is that? These oxidation states depend upon the nature of combination of transition metals with other elements. Let's take an interesting fact related to transition elements. Generally, ionic bonds are formed in lower oxidation state transition elements, whereas covalent bonds are formed in higher oxidation states.
Oxidation states of the first row transition metals are shown here. In spite of all these things, a common oxidation state is seen in the first transition series of d block elements. The most common oxidation state of elements of first transition series is +2.
Students, now it's time to discuss magnetic properties in them. Magnetic properties. Students, as we have discussed that transition metals generally contain one or more unpaired electrons in the N-1 d orbital. With the help of these electrons, we can easily understand magnetic properties in them. Those d block elements which have unpaired electrons behave as paramagnetic substances. These substances are attracted by the magnetic field. Which factor influences this paramagnetic character? Yes, absolutely correct. The paramagnetic character depends on the number of unpaired electrons in d block elements. If the number of unpaired electrons increases, the paramagnetic character increases. If the number of unpaired electrons decreases, the paramagnetic character decreases. There are some d block elements which have paired electrons. They behave as diamagnetic substances. These substances are repelled by the magnetic field. आओ d block elements ਦੇ ਇੱਕ ਹੋਰ characteristic ਨੂੰ ਲਈਏ. Formation of colored compounds. This is most of the transition elements form colored compounds both in solid state as well as in aqueous solution. Can you answer why they form colored compounds? This is because of the presence of unpaired electrons in the outermost d orbital. It is already studied that the transition metals have incomplete d orbital. What really happens?
Have a look at the energy level diagram of d orbitals on the screen. 5 d orbitals are depicted in a free ion. These are degenerate orbitals. When the anion or ligand approaches the transition metal atom or ion, splitting of d orbital into two sets of energy levels takes place. Out of the 5 d orbitals, 2 are at high energy level, whereas 3 are at low energy level. This is called crystal field splitting. Energy difference between two energy levels is shown here. The electrons get promoted from a lower energy level to a higher energy level. But this process requires some energy. The radiations of light are absorbed in the visible region. The compounds absorb a particular color from the radiation and the remaining ones are emitted and thus appear colored.
Let's take an example to clear the concept. Now, the formation of purple colored TiH2O whole 6 3 positive complex can be explained on the basis of crystal field splitting theory as follows. In ground state, the electrons are present in lower energy level, but on absorption of yellow wavelength from visible region of light, the blue and red light will be transmitted and thus solution of TiH2O whole 6 3 positive will appear purple, which is the mixture effect of blue and red colors.
Various factors affect the splitting of d orbital. These are oxidation state of a central ion, nature of a ligand and shape of a complex ion.
Now let me ask you one question. Why copper ions are blue in color whereas zinc ions are white? Copper ions have incomplete d orbital and the electrons are promoted from lower to higher energy levels by absorption of energy. That's why copper ions or Cu 2 positive are bluish green in color due to absorption of red light wavelength. Zinc ions Zn2 positive have completely filled d orbital. It cannot absorb radiation and hence zinc salts are white.
We are looking at a transition metal scandium, that is Sc, on the screen. Its atomic number is 21 and its electronic configuration is Sc 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2. Scandium metal forms scandium tripositive ion by losing 3 electrons. Thus, electronic configuration of scandium ion is Sc3 positive, 1s2, 2s2, 2p6, 3s2, 3d6, 3d0, 4s0. Electrons present in 4s orbital in scandium are 2, whereas electrons present in sc3 positive are 0. Electrons present in 3d orbital in scandium is 1, whereas electrons present in sc3 positive are 0. As you are looking at a complex formed between scandium tripositive ions and 6 water molecules as ligands, it has no electron in its 3d orbital. That's why ScH2O6 3 positive is shown colorless here. Ti4 positive ions also have no electron in 3d orbital. As you are seeing, TiH2O6 4 positive is also colorless.
आओ D block elements which zinc ਤੇ ਨਜ਼ਰ ਮਾਰੀਏ। Zinc ਦੀ electronic configuration ਵੀ ਇੱਥੇ ਦਰਸਾਈ ਗਈ ਹੈ। 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Electronic configuration of zinc ion is also shown here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, 3d10. It has 10 electrons in its 3d orbital.
For Zn2 positive ion, intensity of absorption is plotted against wavelength in nanometer. Wavelength in nanometer is shown here along x-axis. Intensity of absorption is shown here along y-axis. Energy level diagram is also shown here. All d orbitals shown are completely filled. Thus, Zn H2O6 2 positive shown here is colorless. Similar is the explanation for copper ion Cu positive, silver ion that is Ag positive, gold ion that is Au positive, cadmium ion that is Cd2 positive, and mercury ion that is Hg2 positive.
Next is ionic radii. Being metals in nature, the transition elements from cation and their radii as expected are less than the atoms to which they belong.
The radii of bivalent cations, that is M2 positive, are given for comparison, although these elements have tendency to show variable oxidation states as shown on screen. The radius of the ion decreases along the series. This is because with the increase in the atomic number, the effective nuclear charge increases, thereby decreasing the radius of the ion.
Also, the radii of a transition metal ion decrease with the increase in the oxidation state. For example, ferrous ions or Fe2 positive has ionic radius which is equal to 76 picometer, and ferric ions or Fe3 positive has ionic radius which is equal to 64 picometer. आओ D block elements ਦੇ ਇੱਕ ਹੋਰ characteristic ਨੂੰ ਲਈਏ, ionization enthalpies. The ionization enthalpies of the transition metals are higher than those of S block elements and less than the elements of P block. Thus, these are less electropositive than the elements of S block. At the same time, more electropositive than P block elements in the same period.
The values first ionization enthalpy, second ionization enthalpy, third ionization enthalpy for elements belonging to first transition series are shown in the table. In the transition series, the ionization enthalpies increase from top to bottom. However, the gaps in the values of two successive elements are not regular.
The increase in ionization enthalpy is primarily due to the increase in nuclear charge, which would tend to attract the electron cloud with greater force. Thus, ionization enthalpy is expected to increase. As the transition elements involve the filling of electrons in n-1 d subshell, this increases the screening effect. Thus, the effect of increasing nuclear charge is opposed by the increase in the magnitude of screening. So, the increase in the ionization enthalpy of the transition metals is very limited. The last element, zinc, has comparatively high value of ionization enthalpy because it has symmetrical and stable configuration due to the presence of all filled orbitals. Students, now it's time to discuss catalytic properties in them. Catalytic properties. The transition metals and some of their compounds act as catalysts in many chemical reactions. A few typical catalysts and the process catalyzed by them are listed. Vanadium pentaoxide or V2O5 is used in contact process for the manufacture of sulfuric acid. Finely divided iron and molybdenum are used in Haber process for the manufacture of ammonia. Finely divided nickel powder is used in hydrogenation of unsaturated organic compounds, for example, in the manufacture of vanaspati ghee. Manganese dioxide or MnO2 is used as a catalyst in the decomposition of hydrogen peroxide. Cobalt salts catalyze the decomposition of bleaching powder. Reasons for catalytic activity of transition metals and their compounds. The ability to adopt variable oxidation states and to form complexes. For example, during the conversion of sulfur dioxide to sulfur trioxide, vanadium pentaoxide is used as catalyst. In the reaction, vanadium changes its oxidation state from +5 to +4 and then again to +5 as shown. Transition elements can also provide a large surface area for the reactants to be absorbed and thus acts as a surface catalyst. The presence of unpaired electrons in their incomplete d orbitals and thus the capacity to absorb and re-emit wide range of energy makes the required energy of activation available and hence act as catalysts. Next, we will talk about formation of interstitial compounds. These are formed as a result of the trapping of atoms of small elements like hydrogen, nitrogen, carbon, boron in the crystal lattices of certain metals. These are non-stoichiometric in nature and are neither ionic nor covalent. Few examples are titanium carbide, tetramanganese mononitride, triiron monohydride, etc. Another is formation of alloys. Formation of alloys. Transition metals form a number of alloys. Such alloys are hard, high melting points, more resistant to corrosion than the pure metals. In these alloys, properties such as malleability and ductility are lost. Some examples are brass, which is an alloy of copper and zinc. Tungsten steel, which is alloy of iron and tungsten. Chrome steel, which is an alloy of iron and chromium. The reason for formation of alloys is due to the very similar atomic size and hence the crystal lattice of transition metals. So, atoms of one metal can be replaced with atoms of another transition metal, resulting in the formation of solid solution or alloys. ਬੱਚਿਓ, ਮੈਨੂੰ ਉਮੀਦ ਹੈ ਕਿ ਤੁਹਾਨੂੰ ਅੱਜ ਦਾ ਇਹ ਪਾਠ D block elements ਕਾਫੀ ਦਿਲਚਸਪ ਲੱਗਿਆ ਹੋਵੇਗਾ. Thank you for your attention. Till then, bye.